right, guys. So, I hope that y'all had a great break. What we're doing today and most of this week is going to be matrices. So we're going to cover chapter 4 out of the Green Book. So GB, Green Book, because it's the old textbooks that we had before, the ones that we're currently using. The new ones are following the new standards, and the new standards got rid of matrices as well as conic sections. So the last thing that we're covering this semester is matrices. We're getting a little bit deeper into them, and conic sections. Now what we're looking at today is matrices. Now we've covered matrices before, and the packet that we're going through today is not as massive as it portrays, because if you notice, that packet is entirely one-sided, not two-sided. Because I started it running the prints and then realized as it was about halfway through that I only printed it one-sided to one-sided instead of one-sided to two-sided. So it's actually half the size it actually is. Now the first thing we're looking at is this here. So when we organize data in a matrix, it's a rectangular array of constant terms in rows and horizontal rows and vertical columns. So for this matrix here, we have 3 rows and 4 columns. And we can use the rows and columns to describe the matrix as its dimensions. So for this one here, its dimensions are 3 by 4, rows by columns, down and over. So we have 3 down, 4 across, so the dimensions of this matrix would be a 3 by 4. And that's something we've already covered, because we talked about dimension last time. One thing that's new is we actually have something called elements. So each number in the matrix is defined as an element, row by column. So for this here, as it's pointing to the -1, let's get an actual pen. So the element -1 is in the second row, first column. So we define this as A21. Little a, the lowercase of the version or whatever the matrix is talking about the elements. We'll define matrices as capital letters. So this is matrix A, so little a21 is saying second row, first column. And you can think of it as always starting in the upper left-hand corner. So 2, 1. Here. Or if we said 2, 2, so we go down 2, over 2. So a little 2 is element 3. Questions on this here so far? So let's look at this first example. So the first thing it wants us to do is state the dimensions of A. So what would be the dimensions of matrix A? Two and 3, so it's a 2 by 3. Dimensions of matrix A is a 2 by 3. 2 rows, 3 columns, over and down. Now we want to find the value of element A21. Second row, first column is 9. Down 2 over 1 gives us 9. Questions on this here? We're ready for the next one. Now we want to state the dimensions of matrix B. Matrix B would be a what? 3 by 2. 3 down, 2 over, so this is a 3 by 2. Now we want to find element B, 3, 2. As we would go down 3 over 2 and get -1. Any questions on any of this here so far? We good with this here? Let's look at the next one. Now we do have some special matrices, or certain matrices that have a special name to it. So the first one here is a row matrix. When it has exactly one row, we call it a row matrix. Now, it doesn't have to have 4 columns. It can have as many columns as we want. It just has 1 row. We also have something called a column matrix because it has exactly 1 column. Those aren't too important. I mean, it's nice to note, but they don't come up as often or as much emphasis on those. The next one, the square matrix, is kind of significant. And really, it's going to be a square if it has the same number of rows and columns. And those we can do a lot with. So it's considered to be a square matrix, and the number of rows and columns are the exact same. So here we have a 2 by 2. A 3 by 3 would also be a square matrix. And this here is a 0 matrix where every element is 0. Now, just because all the elements are 0 does not mean this is going to be the exact same as this here. Because the one that I drew in is a 0 matrix, but the number of rows and columns are both 1, yes? That is different than one that has all zeros, but is 2 by 3. Because the elements that it composes do make them different. That a 1 by 1 matrix is not the same as a 2 by 3 matrix, even if they're all 0. Does that make sense? Yes? Questions on any of this so far? Addition, subtraction, and multiplication are what we're going to do next. So adding 2 matrices together. We can only add or subtract 2 matrices if the dimensions are the exact same. So here we're saying A plus B. So what we're saying is we're taking matrix A, which is 16, 2, -9, 8, and adding to it matrix B, which is -4, -1, -3, and -7. We're adding these 2 together. Now we add or subtract the corresponding elements. So A, 1, 1, first row, first column is 16, and we would add to it matrix B, 1, 1. But really, we're saying that we're having 16 plus -4. Then we'd have 2 plus -1. Then we'd have -9 plus -3, and 8 plus -7. Now we know for certain we can add these together because matrix A is a 2 by 2. Matrix B is also a 2 by 2. So since the dimensions are the exact same, we can add them together. Now we just need to simplify. 16 plus -4 is 12. 2 plus -1 is 1. -9 plus -3 is negative and negative combine. And 8 plus -7 is 1. Questions on this here? Well, when we did this the first time, because we did these by hand already, but then we also did these in the calculator. Because the first thing we can do in the calculator is say second matrix, and I can go over to edit. Our first matrix, matrix A, is a 2 by 2. So we put the dimensions in 2 by 2, and it gives us a nice little grid. Then we can do 16, 2, -9, and 8. And whenever we plug in a negative number, we'll have to use the negative. We can't use the subtraction. It will throw a fit. And once we get the first matrix plugged in, we can go second quit, second matrix, back over to edit, but this time we'll select matrix B. And this one here is a 2 by 2. So this time we have -4, -1, -3, and -7. Yes? Most of this coming back on how to type the matrices in. We can go second quit. Now we can say second matrix A, because the first list that comes up lets us recall, plus second matrix, this time we'll go down to B, to get the exact same answer. Questions on this here? Let's look at the next problem. B minus C. So we could do this by hand or we can do this in the calculator. So we can pull the calculator back up. Exactly. So there is no way for us to do this. Now, even if we do, because if we notice that it doesn't work, we can say this does not work. Because matrix C is a 2 by 1, matrix B is a 2 by 2. Since the dimensions are not the same, we can't add or subtract them. Now, if I wanted to, we can say 8, 6, and plug that in. And in the calculator, we can say second matrix B minus second matrix C, because that's what we have, B minus C, yes? Enter. Dimension mismatch. It's telling us it's an error. Check size, dimension of list of matrices. Because again, as we said, for addition and subtraction, the dimensions have to be the same. So for this here, it is not possible. Because for us to be able to add or subtract, the dimensions have to be the exact same. Questions on this here?
Nope.
We ready for the next one?
Yep.
A plus B plus A. So we could do this in one of two ways. Now for us, the matrices A and B are the same, yes? So I could replace A, B, and A with their matrices, add the corresponding elements together, and go from there. Or, since I already have them plugged into the calculator, I can say second matrix A plus second matrix B plus second matrix A. And that's it. Questions on any of this here? No. 28.3, negative 21.9. Are we good with addition and subtraction? All right. Let's look at the next part. Scalar multiplication. Scalar multiplication really is saying that we take whatever that scalar is, that number, and multiply it by everything inside the matrix. So when we say 5R, we're saying 5 times the matrix R. So we're multiplying all the elements of matrix R by 5. Because if we say 5R, we're multiplying the entire matrix by 5. So the first thing we can do, or what we're really saying, is that we have negative 12 times 5, 8 times 5, 6 times 5, negative 16 times 5, 4 times 5, and 19 times 5. Negative 12 times 5 is going to be negative 60. 8 times 5 is 40. 6 times 5 is 30. Negative 16 times 5 is going to be negative 80. Yes. 4 times 5 is 20. And 19 times 5 is going to be 95. And that's it. Now we could have done this in the calculator, because I could have typed matrix R in and then 5 times R and got this here. But for some of these, make that 8 a little bit clearer, it almost would have been just as easy to do 5 times each one of the elements and got it just as quickly. Questions on this here? And matrices do show up on the ACT a good bit here and there. We ready for the next one? So for this one here, we're just multiplying everything by what? Negative 4. So we're saying negative 4 times 8, 0, 3, negative 2, negative 1, negative 4, negative 2, and 9. And really, we could go through and either type the matrix into the calculator and say negative 4 times matrix A, hit enter, or we can just do negative 4 times each one. So we could say negative 4 times 8 is negative 32. Negative 4 times 0 is still 0. Negative 4 times 3 is going to be negative 12. And negative 4 times negative 2 is just 8. Then negative 4 times 1 is going to be 4. Negative 4 times negative 4 is 16. Negative 4 times negative 2 is 8. And negative 4 times 9 is negative 36. That's it. We're just multiplying each of the elements by negative 4. Yeah. Questions on any of this so far? We good? Now, just having scalar multiplication, doing that's not too bad by hand, or just doing each one in the calculator. Now, the commutative property of addition holds true with matrices. A plus B is going to be the same as B plus A. Just with most addition, that holds true. Associative property of addition holds true. I can add any three things in any order and get the same answer. Scalar property, scalar distributed property, I can multiply a scalar through on the left or right, it doesn't change it. These hold true in any order. Now, we can combine addition, subtraction, and scalars. Now, doing this by hand is a little, not difficult, but we can either, especially with the second one, negative 3a, I can multiply matrix A by 3 and then subtract the 2. Or I can multiply everything in it by negative 3, but if we multiply it by the negative 3, then we would need to add, because we took the negative with it, and we would just add them together. Or there's the other option of plugging this in, because we do have matrix A and B, yes? So in the calculator, the graphing calculator, I can go second matrix, over to edit. And matrix A is A2 by 2, because we have negative 9, 12, 2, and negative 6. I can go on and plug matrix A in. Questions on this so far? Then we can go second quit, second matrix, over to edit, and go down to matrix B, which is also a 2 by 2. It's negative 4, negative 8, 2, and negative 3. Questions on how we type these in? Now at this point here, we can say second quit. Now the problem that we have is negative 4b minus 3a, yes? So the first thing I can type in is negative 4. And then we call it matrix B. So second matrix B minus 3 second matrix A. And there's the answer. Questions on how we got this answer? So the answer for this here is 43, -4, -14, and 30. Questions on doing these? We kind of like addition, subtraction. Even with scalars, it's not making them any more difficult. If we do them by hand, it does take a little bit longer for distributing the scalar through and then simplifying. The calculator will do it for us. Last thing we have is matrix multiplication, multiplying two matrices together. Now, for us to be able to multiply the matrices together, the columns of the first has to match the rows of the second. The columns of the first has to match the rows of the second. And the rows of the first and the columns of the second will be the new dimensions. So the rows of the first, or sorry, columns of the first and the rows of the second have to match to be able to multiply. If those are the same, then we can multiply the two matrices together. The rows of the first and columns of the second will be the dimensions of the new matrix when we multiply them together. So with matrix multiplication, the rows and columns of both don't have to be the same. They don't have to have the same dimensions. So let's look at this here. So for the first four that we're going to do, these here, we're not going to actually multiply anything together. We're just going to determine if multiplication is possible. So if I'm multiplying A and B, A times B. So when we look at this here, the columns of the first, does it match the rows of the second? Yes. So can we multiply these together? Yes. Determine whether each matrix product is defined. Yes. So it is, and the new dimensions of A times B is going to be rows of the first by columns of the second. So our new dimensions are going to be 3 by 2. Questions on A? Let's look at B. Can I multiply A and B? Because if we look at the rows of the first, or columns of the first and rows of the second, 3 and 5, they're not the same. So, not possible. Let's look at 1A. Can we multiply these together? Because the columns of the first is 6, the rows of the second is 6. So yes, we can multiply these two together. We'd have A times B. And our new dimensions are going to be what? 4 by 2. How about 1B? Columns of the first is 2, rows of the second is 3, so this is... For 1B, could we add those together? Yeah, 3 by 2 and a 3 by 2, they do have the same dimensions, so we could add them together. Okay. When we multiply two matrices, the way I think about it is over and down. So when we multiply a 2 by 2 and a 2 by 2, we go over and down. We do A times E and then B times G and add those together to get our first one. And we do the same thing. We go over and down to get our second row first column. C times E, D times G. We're going over and down, over and down. That's why the number of columns has to match the number of rows, are over and down. So this seems a little weird, seems a little confusing, but when we actually do the multiplication, it's going to make sense. So here, we're multiplying x, 6, -3, -10, and -2 by -5, -4, 3, and 3. Bless you. So we're going over, down, over, down. So we look at this first part here. So the first thing we're going to do is go over and down. So we're going to have 6 times -5 plus -3 times 3. Questions on this so far? So we went over, down, matching up, multiplication. We good with this so far? We're going to do it again. We're going to go over and down. So we'll have 6 times -4 plus -3 times 3. Any questions on how we got the first row of our multiplied matrix? Are we good with this here? Now we're essentially just going to repeat the process with the next row. So we'll have -10 times -5 plus -2 times 3. Questions on this here? And lastly, over and down. So we'd have -10 times -4 plus -2 times 3. Now we just need to simplify each of these. So when we look at the first one, -5 times 6 is going to be -30. -3 times 3 is -9. Next one, 6 times -4 is going to be -24. -3 times 3 is, well, -9. We go to the next one, -10 times 5 is +50. -2 times 3 is -6. And lastly, -10 times -4 is 40. -2 times 3 is -6. And lastly, we just need to simplify this here. So you can write it underneath or out to the side, either one. -30 minus 9 is going to be -39. -24 minus 9 is going to be -33. 50 minus 6 is 44. And 40 minus 6 is 34. That's it. Questions on this here? And if we wanted to, we could have plugged this in a calculator. It can do it as well. Because I could say second matrix A, which is a 2 by 2. So here it's 6, -3, -10, -2. Second quit, second matrix B is a 2 by 2. So -5, -4, 3, 3. Second quit. Second matrix A, second matrix B. A times B, if we put them next to each other, it is considered multiplication. And he gives us our answer. Questions on this here? Questions on any of this so far? Now, say we did B times A, because we know matrix or multiplication so far is closed under a commuted property. We can multiply any two things in any order, yes? So if we flip the order of this here, yep, we get the same answer, yes? No. Because the process for multiplying, we're going over and down. We're not multiplying the same things. So the commutative property for multiplication with matrices is not closed. It doesn't actually exist. So the order in which we multiply two matrices matters. Questions on this here? Any questions on any of this so far? We good with all this here? Okay. So your homework for this here, because there's other problems and it's just going through kind of showing that the distributive property with matrices is not closed. So if we multiply something on the left, it has to be on the left or on the right, because it is not closed.